We talked about inelastic relations being the most common kind of relations, right? Because this is where you have momentum conservation. So that holds, which means momentum before and momentum after is the same. But kinetic energy conservation is not dated. So in elastic cases, as I discussed last time, the energy conservation or kinetic energy conservation in this case is not dated. And one example I gave was that of firing of a rifle, for example, where you have something at rest before you fire, and then when you fire, so initially everything is at rest, there is no velocity involved, so momentum initially is zero, because you have let's say you have a mass of the rifle, let's call it an R, and you have a bullet in there, let's call it small m b. So clearly, the two masses are both at rest, so initially momentum, let's say initial momentum, that is equal to zero, because nothing is moving. That's pretty easy. Now what happens is that you fire this. You're not interested in the moment at which you are actually pulling the trigger and so on. But then you see what's happening. And what you see is that this bullet is now traveling forward, because this bullet has now come out and is taken off. At some velocity, let's say v bullet. And the rifle is going to have to recoil, because think about it. You have no momentum initially, momentum is conserved, momentum before and after is the same. You have a mass of the bullet times the velocity of the bullet, and these are all positive. So if the bullet is going to the right, that's the right side is positive. So then as far as the rifle is concerned, you must have a mass of the rifle and a velocity of the rifle to get the momentum in there. But the only way this is going to work out is if this velocity is in the opposite direction. So therefore, what will happen is that if you take the position of the rifle will be going back. Going back by how much? Going back by how much will actually depend upon the mass of the rifle and the mass of the bullet, as well as the velocity with which the bullet is being shot. If the velocity is large, the recoil is going to be large. If the velocity is small, the recoil may not be so much. So, what we are not talking about is that the rifle is typically held by a person. So this person is going to feel the recoil. The person will recoil with the rifle. If this is a person with some formidable mass, the recoil is going to be relatively small, depending upon the numbers. But if it's a small person, then this recoil is going to be quite large. So recoils can be quite an effect in bigger rifles. So I did work out a problem, which is in your notes, which you can look up, with some numbers onto this recoil problem. And basically, the kind of numbers I use would be like this. So, I think I wrote it down last time. But let's say this M rifle, which I wrote somewhere, this M rifle, let's say, is 3 kilograms. Yeah. The M rifle is 3.00 kilogram. Let's say mass of the bullet is 5 grams. So that would be 5.00 times 10 to the minus 3 kilograms. You're going to convert it to kilogram, obviously. Let's say the velocity of the bullet is about 300 meters per second. So this number here is 300 meters per second. Then what you have is that you can calculate the velocity of the rifle, and the velocity of the rifle, which I call VR, will come out to minus half a meter per second. So these are some numbers. Now, why am I giving you the numbers? The reason why I'm giving you the numbers is because I want to show you that while momentum conservation should work, and it does work, let's say, This one does not work. Kinetic energy conservation is not reached. Now it's very easy for us to see that. The way to see that would be initially how much is the kinetic energy in the system? Zero, because nothing is moving, right? So you don't even have to do a calculation because kinetic energy cannot be negative, right? It's half mv squared. It cannot be negative. So kinetic energy, therefore, after you fire the bullet, with the rifle recoiling and the bullet going forward, cannot be zero anymore. So therefore, kinetic energy before and kinetic energy after cannot be the same. So you can actually do a calculation and you'll find that the total kinetic energy after firing, and this will be, let's say, equal to Ke after, just so we know. So it's 1/2 mass of the bullet, the velocity of the bullet squared, because that's the definition of kinetic energy. 1/2 mass of the rifle, or I call it a big mass, and the velocity of the rifle squared. If you do the numbers, then what you get is a pretty large number here, 285.4 joules or so. So as you can see, kinetic energy before and kinetic energy after are quite different numbers. Kinetic energy conservation doesn't work here, and that's why it's an example of inelastic collision. What is an example of a perfectly inelastic collision? Two things get stuck. If two things are getting stuck, that's a perfectly inelastic collision. The advantage of a perfectly inelastic collision study is that you know that in one case, both masses are lumped up together and moving together. That is the main difference between a perfectly inelastic collision and a normal inelastic collision, which is a more common kind of inelastic collision. So this is one kind of inelastic collision, but if I move one block against the other block, and the two blocks get stuck and start to move, then if they do get stuck, that is a perfectly inelastic collision. There also, this kinetic energy conservation will not hold. Now, there is a very classic problem, so let me just show it to you. And this is called, this is an inelastic collision, completely inelastic collision problem. So it also is illustrated. Since we are doing momentum collisions, momentum conservations, one dimension, things are not terribly difficult. But things do get a little hairy once you get to two dimensions. And I've avoided doing two dimensions so far, but I might give you a homework or two just so you have some exposure to it. So the ballistic pendulum then goes like this. The idea of a ballistic pendulum. So ballistic pendulum is typically to figure out the velocity of a bullet. So a bullet is fired, and the fired bullet is supposed to get stuck. That's the way it's designed, in a wooden block. So this wooden block is a well-characterized wooden block. So let's say it has some mass, M, and I call it MW because it's a wooden block. Whatever the number is, it's quite a large number. And then there's a bullet coming from here. Mass, small mass, mass of the bullet, let's say, and moving at some velocity v bullet. This one is not moving, so this one is at rest. So now what happens is that this guy comes. So next instance, what happens? What happens is, so this is initially, and finally what happens is that you have the ballistic pendulum here. So I'll draw two versions of it. Say I have one version like this, and in this case, the bullet, let's say, has just come in and got stuck somewhere inside. Okay? So now you have an example of a perfectly inelastic collision because this bullet has gotten stuck. inside the wooden block. So what you have here is that mass of the wooden block plus mass of the bullet. Okay? So initial momentum was, initial momentum, let's say, I'll call it momentum, is equal to mass of the bullet times the velocity of the bullet. I take the right direction to be my positive direction. That's the initial momentum. This guy doesn't have any momentum because this guy is not moving. The block's at rest. So there is no momentum contribution coming from the block. So therefore, this is my initial momentum. Now what will happen is that momentum conservation will demand that because this thing has gotten stuck here, this is going to move. Right? That's what it moves. So if it moves, how will it move? It has to go up because it is a pendulum, right? So let me exaggerate a little bit just to be clear what we are talking about. So let's say that this bullet is moving pretty fast and this thing has raised to some level. I just keep things looking pretty simple. It's kind of some level like this, it will actually tilt up. But let's say it doesn't tilt up too much. So now, after a little bit of time, this has swung up to a high point. So what is the, so once this gets stuck, let's give this a velocity v with which it's going to move. And let's say this velocity v is big V. Okay? So momentum conservation implies that mass of the bullet times the velocity of the bullet must be equal to mass of the bullet plus mass of the wooden block plus this big V, which is the velocity of the composite system, the block plus bullet system, immediately after collision. So at this point, what one does is one measures this thing. As it starts to move, let's say you can measure it. If you could measure it, then you could immediately write the velocity of the bullet, which is something you want to find out, as m bullet plus mw divided by mass of the bullet times this velocity. So that's one thing. So you can relate the velocity of the bullet to this big V. But now suppose you couldn't measure V. All hope is not lost. Because as this thing swings up, it gets up to a certain height with regard to the center of mass level of this guy. Or whatever. I mean, basically, this wooden block rises by a certain amount. You can take a symmetry point in the middle of the center of mass and you can find it. So let's say the height is h. It is risen by height h. What would be the potential energy for something rising by height h in this case? Come on. mg. Yeah, so you have two masses. So potential energy gain, the potential energy, let's say, let's give this point a name. Let's call this point, let's call this configuration, let's say, A. Let's call this configuration B. The potential energy at B is clearly going to be two masses, m bullet plus m wood times g times h. H is easy to measure, so it's much easier than measuring the velocity of the moving thing. So this is the potential energy at B. This potential energy obviously came because there was an initial kinetic energy that came around from the block. That will be 1/2 m bullet plus m wood times g squared. Okay? So immediately that tells you that the masses wouldn't matter, and I should be able to write this V as 2gh squared root. Okay? So therefore I should be able to write this bullet velocity as m bullet plus m wood divided by m bullet. And then to the image. So that's the problem. In other words, just by measuring the height by which this wooden block and the bullet combination has been raised, by taking advantage of completely inelastic collision and momentum conservation, as well as energy conservation, which is what we have done here. We have used energy conservation here. We can actually solve this problem rather nicely. So this is the solution. So I can write VB as MB plus MW over NB times root over of 2GH. Now, so there is something interesting going on in this problem. I said it's a completely inelastic collision, right? Is energy conserved in it? Energy is not conserved. So why did I get by using energy conservation as far as the complete system is concerned after the bullet was stuck? Why do you think that was okay? Why was it? What happened? Did I do something wrong? If you did this, would I give you a 0? No? Come on. Yes.
You use conservation of energy to prove that the energy loss is converted into potential energy.
Not quite. But that was a brave attempt. Anybody wants to make a brave attempt? This is important. It requires you to think. Yes, John, James.
The potential energy doesn't zero. Kinetic energy doesn't have any goes to things, so that based on certain amount of energy, energy is.
Well, the two together make mechanical energy. Mechanical energy. Question really is whether mechanical energy is conserved or not. Initially, during the collision, where the bullet got stuck with the wooden block, mechanical energy was not conserved because that was a completely inelastic collision. But I still used mechanical energy conservation post-collision. Why was that? Why was that not illegal? Yes. Say a little louder. Okay, yes. Okay, I think some of you are converging to the right. First of all, momentum is conserved and energy is not conserved as far as the collision is concerned. There's no question about that. But when the two get stuck, at that point, as the whole business about conservation of momentum and inelastic collision is done, you have a different system, if you will, which is the block plus the bullet system, right? As far as the block plus the bullet system is concerned, this one gets moving. So once it gets moving, you can definitely compute its kinetic energy. Whether it's useful or not remains to be seen, but we can compute its kinetic energy, and there is nothing fundamentally wrong with doing it. So it's half that mass times the velocity squared, which is something that I gave this name big B, right? So this thing can be computed. Now the fact is, this whole business now, you can't stop it from swinging up. And we don't really have any dissipation that we are taking into account as far as the swinging up is concerned. So this second part of the problem is actually somewhat completely different problem, where the whole thing is swinging up. And because it is swinging up, it is gaining potential energy, and finally it stops at a certain level. So you have a potential energy which is the sum of the two masses times. So that's basically the problem. So this problem actually has two sub-problems in it. First is the momentum conservation problem, That has to do with completely inelastic collision aspect of the problem. The second is you have a situation where you have an energy conservation problem that actually works out just fine. Okay, so this is the point. Did you guys get it or no? All right. Let me now move on to something that I teased a little bit about last time, and that is the center of mass. Now we all have some idea of the center of mass, even if you don't know what the center of mass is. Chances are that your brain knows quite well, because if you did not know your center of mass, you would have still been a toddler. So the very fact that we grew up from being a toddler to being an adult, or being able to walk alone, not really adulthood, that was around age 1 or 2, meant that your brain figured out the center of mass, right? So why do toddlers easily become unstable? You realize why? Why were you unstable when you were a toddler? Yes.
They have pretty big heads
Which means
that
yes.
They're top heavy, so.
They're top heavy, that's right. That's what you meant. But so if you think about it, because when we are little, we have very big heads, our center of mass is high. And if the center of mass of something is high, then if that thing is moving, the tendency for it to wobble is obviously going to be higher. That's the problem. So now when we grow up, proportionately we become more stable, because the size of our head doesn't increase so much. We all have the same brain size, about 1700 some cc, I think. So brain size is fixed. The size of the head is more or less fixed. But as far as the body is concerned, the body grows, and so your center of mass relatively is now actually a little bit downward. It's way below being near the head, and that really changes things a little bit. Okay, so that's why we become more stable. So the idea of a center of mass is important, because when we are dealing with a solid block, let's say whatever the solid block is, we can replace whatever is in the solid block, the entire mass in the solid block, and this is something I discussed in the very first lecture, by basically what we call a mass point. A mass point, implicitly, is, in our imagination, all the mass of the solid block is concentrated in one point. So thus far, we have not considered objects in which we have to do any more thing than assuming it to be a mass point. We didn't have it. That was completely unnecessary. However, now this will become important, because now we'll be dealing with extended objects. And extended objects can be not that simple, so you have to be a little careful. What would be an example of an extended object? Well, something like a wheel would be an extended object. And it may be true that if you're considering the rotational motion as well as the fact that a wheel is going forward, this whole problem, and something that requires you to take into account that you are dealing with an extended object. In fact, it will. And we'll come to this problem. This problem is quite interesting and quite complicated. Similarly, if you get on one of those, whatever we call them, merry-go-round or something, that would be a disc like this, and the disc is turning, and you know very well that this is a fun thing to do if you know what you're doing, right? If you don't know what you're doing, bad things can happen to you. You can fall and you can hurt yourself. So if this thing is going around, and if you're trying to get onto the merry-go-round, where do you think you want to get onto the merry-go-round, just to be safe? Huh? Yes. Why is the center a better place than the edge? Huh? Well, all right. You can think of it in a variety of ways. We'll come to an explanation of that, right? But you can immediately see that the extendedness of the shape is becoming important, right? If you're getting onto a merry-go-round, and if you get onto the edge of a moving merry-go-round, chances are you'll become unstable pretty quickly. But if you hop in somewhere near the center, which may not seem like a safe thing to do, but it turns out that it will actually give you more stability. So extended objects are a little bit different. At any rate, before we get to a treatment of extended objects, we realize first that we are dealing with extended. Now, extended objects can be quite messy, right? For example, the water in the bottle here is also an extended object, right? So if I tilt it, the way the atoms and molecules are arranged changes. If I tilt it further, so whatever the angle is, how they are situated, the atoms and molecules will change. So this is an extended object. If I shake it, things will go all over the place. So extended objects can be quite complicated. For instance, if I take, instead of water, if I take some jello, that will be very floppy. So we will talk about rigid extended objects. Just to simplify matters, such that we are not dealing with systems where things can move around. So it's a rigid extended object. So let's now define the center of mass of a rigid extended object. So the mass points that make up some shape, let's say, they are in fixed positions with respect to each other. So it's a rigid object, but it does have an extended shape. So in this case, let's say it's some body. It doesn't have to be necessarily symmetric. I want to find out what is the center of mass of this object. This is quite easy to do. You set up your axes somewhere, all right? So this is a three-dimensional object, so I need an x-axis, a y-axis, and a z-axis. So I need to make measurements about the x position, the y position, and the z position of every mass point that makes up this extended object. It's only by measuring where every mass point, which means every atom, is located, will I have a chance of correctly finding the center of mass. So that is how it works. So that's not an easy thing to do, and we all know that, which is why finding center of mass is complicated. So x center of mass, which is the x coordinate of the center of mass, can be thought of or defined in the following way. Let's say I have a total of n atoms that make up this solid object. So I sum I from 1 to n. I is an index that goes with every atom, and then the x position of every atom. And I divide that by the sum of all the atoms, because at the end of the day, this is the length. This is the mass times the length, and I'm going to divide by mass. So therefore, I can write this as 1 upon big M, sum over I, mi, xi, where I runs from 1 to n, whatever. So my big M is obviously the total mass, so it's sum over all the atoms. So I can write it like this. This would be a very accurate way of writing things. And similarly, I can also write a y center of mass and a z center of mass. So that would be 1 over m again, because here there is no directionality, but sum over I is 1 to n, mi by I, and this would be 1 over n, sum over I is 1 to n, and I z. Okay? So this is how you would find the center of mass. Now, so as you can see, finding the center of mass something not a symmetric object can therefore be pretty difficult to do. So let's say, now some of the center of mass calculations should be quite easy, right? Because if I have a T like this, I can easily tell that if this is made of material that is uniformly distributed, so let's say it's a thin metal sheet, which is perfectly uniform. Then of course the center of mass of this piece here would be somewhere around here. That's very easy to do. You just find out where the geometric center is, and you are done with it. You know the total mass by measuring the mass, and that's it. You know the center of mass position. Likewise here, if this is a thin uniform metal or something like that, then you know as far as this piece is concerned, let's say exclude here, it will be something somewhere down here. And then you can figure out that which mass is more. This is more or that is more, and then proportionately you can arrive at some center of mass of the whole thing, which is somewhere. That's it, for the sake of argument. So if you knew the center of mass, what can you do to stabilize? Suppose now you are holding this T like this, and you want to make it stable. Where would you put the support? At the center of mass, right? So have you ever seen these airplanes and so on that used to be toys, or sometimes for display where you have an airplane that can be like this, but supported with a tiny little stick? Have you ever seen those toys? Some of you may have, but a lot of you may not have, because I don't see them around very much anymore. But at any rate, that is being supported at the center of mass. So if you actually press on the, suppose this is the airplane, if you press on the airplane, it will wiggle and eventually stabilize and not fall off. So, if I were completely rigid, which I would be if I were totally dead, you lift me up and hold me with a finger, it will work just fine, because my center of mass will be very well defined, I won't be moving, there will be rigor mortis, and you'll be able to hold me just fine with a single finger. You won't be able to do it when I'm moving around, or even when I'm alive, because I'm somewhat floppy. So this is how the center of mass things work. Now you can immediately see this becomes quite complicated if I actually have a fairly messy system like something like this. Now that won't be the most fun thing to do the center of mass calculation of, right? Because it's pretty bizarre. There are center of masses all over the place for each of those pieces, and supporting a thing like that is complicated. So therefore, center of mass calculations can be quite complicated. So how do we deal with it? Well, we have now learned to deal with them. One of the ways you deal with it that you won't be doing is you replace this summation here by an integral. That we won't be doing because we are not supposed to be doing integration. But if you actually replace it with an integral, just for the sake of those of you who know a little bit of calculus, what happens is that all you need to do is now fix the geometry of the substance that you are dealing with. And if the mass distribution is uniform or not. Once you have those two quantities fixed up, you can actually do the integration and you can actually calculate this. That's where calculation comes in really handy, but the summations here that are involved don't really work because that's too hard to do. Alright, so we will only be dealing with systems that are very, very symmetric. Alright? That way we can avoid some of the hassles. Alright. Now, let me now move gears to something which is far more serious than stuff like definition. So I will start what I would call rotational kinematics. At some level, rotational kinematics is quite simple. It's quite simple. It's not at all something that is very, very hard to do. Why is that? Because you guys know kinematics, that's why. The fact that you know kinematics is a massive, massive advantage as we learn rotational kinematics. And the fact that you have learned to do dynamical problems by solving different situations and free body diagrams and what have you, also now becomes your asset as you start rotational dynamics, the next chapter. So why is rotational kinematics important? What is rotational kinematics about? Well, rotational kinematics is basically about the following rotational quantities. So if I have actually a wheel, let's say the wheel is of radius r, and let's say this wheel is turning, and the angle by which this wheel turns, the rigid wheel, the angle by which it turns is some small angle, call it delta theta. Delta theta meaning, again, the small angle theta. The delta meaning is small. So I should be able then to describe this distance traveled by any point on the wheel, let's say a point here, over some time delta t. So this is like an x. Or I can even call it a delta x, just to keep the deltas around, which means a small amount of x. So I should then be able to write delta x is r, which is the radius, times delta t. Okay? If delta x is r delta t. So it's basically like you take the radius and you pull the tip of the radius by delta theta, and that's your delta x. That's how these are defined. Now you can, there is no reason to screw this up, and if you do screw it up, I'll really not be nice. Why is there no reason to screw it up? Because you see, what does delta x has the dimension of? does delta theta have a dimension? Delta theta is an angle. What is the dimension of an angle? Huh? What? Come on, don't mumble. What? How do you define an angle? What happened to you guys? You guys are going dumb on me or something?
Greece?
Yeah, but what is the dimension? Does it have a dimension? Huh? No. No dimension? Is he right? There is no dimension. He's usually right. But is he right this time? There is no dimension? No? So I go from here to here, an angle, right? Does that have a dimension? Is it length? Or is it? If I go around like this, full circle, I come back to the same point. Is there? Actually, it's a little tricky. The answer is there is no dimension to it. So he is right as usual, but there is no dimension to it because angle doesn't have a dimension. This does have a dimension. This is length, and this is length, but this has no dimension. So you see, delta x has to be equal to something like an r delta theta. You don't have a choice because otherwise it will be dimensionally inconsistent, right? Because the equation should be dimensionally correct. So this is the way to remember this relation. That's why I was putting it in the shortcut that delta x must be r delta theta, and you should think like that. So now, if I want to calculate the speed with which it is rotating, let's say v, I can write v as the amount of distance this point travels. It's a rigid quantity, so if I can get this point, I can get any other point. It means the same thing. So this would be delta x over delta t. So that would be r delta theta over delta t. So how the delta theta goes as a function of delta t, this rate of change, is what actually we called omega before, which is the angular speed. We introduced omega before, if you remember, and this is the angular speed or the angular velocity, both by various names. So you can see that you should be able to write x equal to r times theta from this relation if I don't write in terms of deltas, the small angles. And I can also write v equals r times omega. So x is distance, theta is an angle, v is velocity, omega is an angular speed. So you see the relation between the linear quantities like distance and speed or velocity and so on, and the angular quantities in circular motion are to r. So x, the analog of x in circular motion is theta, angle. The analog of speed, velocity, or speed in circular motion is angular velocity. And similarly, if I want to calculate the acceleration would be delta v over delta t. So delta v, so v is r omega, so it's r times delta omega over delta t, and that is what we call r times alpha, where alpha is the angular acceleration, so a is r alpha. So the relation between the linear quantities and the angular quantities goes like that in the box. And they are obviously cousins. They are very, very closely related because you can go from the linear quantities to the angular quantities by correctly multiplying with r. How do you know that you correctly multiply with r? By dimensional analysis. Because this is length, this is length. This is no dimension. This is length over time. This is length. Omega is 1 over time. Does it work? Yes. Omega, you see, is dimensionless over time. So 1 over time. This is length over time squared. This is length. Angular acceleration as units of inverse second squared, or 1 over t squared, t being the dimension of time. Now you see, when you did your regular chapter 2 business, whatever, chapter 2, chapter 3, you did kinematics, right? So as opposed to now what we are doing is rotational kinematics. Okay? So the difference between the two is actually quite nice. So what are the various kinematic equations? Remember we have an equation like this. Distance or displacement x is x naught, if you will, plus initial velocity, let's call it v naught t, plus 1/2 acceleration times time squared. Similarly, I had another relation which was final velocity is initial velocity plus acceleration times time. And I had a relation which is time which doesn't have time. The final velocity squared is initial velocity squared plus twice acceleration times distance traveled. Let's call it x minus x naught. You remember these guys? Old friends of yours? Or you forgot? You forgot that we are in future. I tell you why. Because they come right back at you. So you see x, the equivalent of x is what? Theta. So I can write theta equals theta 0, like x 0. I can write an omega 0 instead of v0 t plus 1/2 alpha t squared. I can write omega equals omega 0 plus alpha t. I can write omega squared is omega 0 squared plus twice alpha theta minus theta. These are your equations of rotational kinematics. So the reason why I was asking you guys so many questions about how to relate x, b, and a to theta, omega, and alpha is because once you know these guys, you can directly go. So you will now have to do rotational kinematics problems, which look and feel very, very different than what you have done before. But from the standpoint of doing the kinematics, linear kinematics versus rotational kinematics, there is a complete one-on-one correspondence between how you go from one to the other. Okay? So again, just to make sure that you don't screw it up, remember then that x goes to theta in rotation, b goes to omega, and a goes to alpha. To make them into equations, you have to multiply with r, the radius, in the way I showed you. Is the angular acceleration same as the centripetal acceleration? Centripetal acceleration is directed towards center. But here when you're talking about angular acceleration, you're talking about, let's say, a wheel speeding up faster and faster, right? So therefore, if you are at the edge of the wheel, the way the velocity is increasing would be perpendicular to the radius, would be that way. So therefore, your angular acceleration is not the same as the centripetal acceleration. So this A that you're going to get, this A, therefore, you can call it, this A is different because, I think I put a name for it. Let me just look at it. I call it tangential acceleration. Tangential acceleration. Why? Because if I have a wheel, and if I go to the edge of the wheel, and this thing is rotating faster and faster, then the tangential acceleration will actually be in this direction, A tangential. Because as far as this particle is concerned, this is a tangent. As far as this particle is concerned, this particle is moving faster and faster. So this is the direction of turning. But the centripetal acceleration that it will face because of its motion is therefore going to be inward. So the net acceleration, which is the sum, vector sum of the tangential and the centripetal acceleration will be, depending upon how fast it's going, somewhere in the middle. That will be a net, the direction of the net acceleration. So you're getting into a territory, as I told you before, where stuff gets really, really hard. Okay? So don't take anything for granted. Chances are that exam 3 will be very hard because you'll have both rotational kinematics and dynamics building up on everything else. So it's very important that you get the material well, and whatever help you need, you seek it in a timely manner. So we'll do some problems on these, but before we do the problems, there's a very important concept that I want you to use. The concept is that of energy, kinetic energy. So let's say that I have a rotating disk. Rotating disks, by the way, are everywhere. Rotating. So most machines have rotating disks in some way. We have talked about the center of mass, right? We have talked about delta, we have talked about theta or delta theta over there in the top right. We have talked about omega, which is angular speed. We have talked about alpha, which is the angular acceleration. These are all kinematic quantities. Now, one of the things that we also need to talk about is how much is the kinetic energy of this guy. Because that will come in front, square, and center, because we would like to be able to use energy conservation in our calculations. So, the only way we know how to calculate the kinetic energy, well, first of all, if it's not moving, it's not going around, its kinetic energy is 0. So let's get that clear. So let's say the radius here is r. But if it's moving, then the kinetic energy should be half times the mass of every particle times the velocity squared of every particle summed up, if there are n. As you can imagine, this is a mess of a thing to do, because the number of particles is very, 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 very large, and therefore, forget about one lifetime, not even in many lifetimes will you be able to actually calculate the whole kinetic energy well. So, kinetic energy is 1/2 mi vi squared. What we can immediately see is that since if it's going around in a circle, if it's rotating, let's say, then I should be able to write Vi as omega I r I. So let's try to understand what we are doing here. So let's say we consider a single particle. Let's say we consider a particle here, or a mass point here, and this is the distance Ri of this mass point, Mi. Okay? So this Ri is that Ri. Alright? This Ri here is that Ri. So clearly, as I take various different mass points, this Ri would change. Would omega I be I dependent? I told you it's a rigid body. So for a rigid body, everybody is moving at the same angular velocity because their relative positions cannot change. They're all stuck in the same position. So therefore, I do not need an omega I. So omega is the same everywhere because it's a rigid body. So for a rigid body, I should be able to write omega I is equal to c omega. It's a constant. Or it may not be a constant, but it's a fixed number. Alright? So I can then rewrite this 1/2 sum over I 1 to n mi vi squared. I should be able to write it as omega squared Ri squared. Okay? omega squared Ri squared. So, since omega doesn't care about I should be able to write 1/2 omega. I can keep the omega outside the sum because there is no I index if omega is not contributing. So I can write I equal to 1 to mi Ri squared. I put that in the bracket. So this is my kinetic energy. Now let us say we want to compare the kinetic energy formula that we have here with the kinetic energy formula that we usually use for most objects. So now what happens is as follows. We are calculating the kinetic energy of the disk. In this case, we load up a disk. And we are saying that this is omega squared over 2, sum over I, mi Ri squared. Now, this is a very complicated sum because you have all these particles that are distributed along the disk. And to be able to sum up the masses of these particles, multiply that with the positions of the particles and square it, is a humongous job. So that summation cannot really be done for all practical purposes. That summation is always replaced by an integral. Again, since we won't be doing integrals, this is not something that we'll worry about too much, but we want to know a few things. First of all, you remember that kinetic energy definition is mass times velocity squared. So for a solid object here, in this case, I can write in the form of omega squared over 2 times some quantity I, where I define this sum as I. This I has a name, yes.
Should omega be squared for the k equals half omega summation m1 r squared?
Yeah, I did b squared. Oh, this is an omega squared. That's what you were saying?
Yeah.
Yeah, that's why square gets resurrected down the road. So you see, there is a striking similarity between this formula here for the kinetic energy of a rigid object and the original formula for the kinetic energy of a particle moving at velocity v. What I'm trying to tell you is that when you have a rigid body, a solid extended rigid body, it doesn't have to be a rigid body, but in this case we are only working with rigid bodies. Then the formula looks the same, except instead of linear velocity, we have angular velocity or angular speed. Both names are used. And instead of mass, we have this I here, which is this guy here, and it has a name. It's called moment of inertia. So moment of inertia is something that depends upon the shape of the object. So if I have, let's say, a stick that is rotating, or if I have, let's say, a sphere that is rotating, or if I have, let's say, a disk that is rotating, or some weird shape that is rotating, maybe still symmetric, then the moment of inertia of all those objects will be different depending upon the shape of the object. The shape does not, if the shape changes, the moment of inertia will necessarily change as well. So therefore, this is something that we got to know. But there is another important point here, which makes things a little bit more complicated than what all I just said. And this is a question for you guys. Get prepared to answer. If you are rotating something, let's say you have a simple thing like a frisbee, okay? And you are putting your finger in the center of the frisbee and just twirling a little bit. It's going around. That's one case. So for a frisbee, normal frisbee, I would imagine that the center of mass of the frisbee would be at the center of the circle, right? Roughly, should. So if you put your finger at the center of the circle, this is your frisbee. This is rotating, this is stable. So you can calculate its kinetic energy using everything I just said. Now suppose, instead of putting my finger smack in the center of mass, I decide to put my finger somewhere else. Let's say near the edge of the frisbee. Do you think that the kinetic energy of the frisbee in both cases would be the same or different? Think about it. Play a little bit of frisbee in your head. What do you think will be happening? Will the kinetic energy be the same as the first time when you put it in the middle, or will the kinetic energy actually possibly change?
It's going to be different. In the middle, it goes faster than when it's the kinetic energy is more than when you have on the outside, more close to the outside.
It will also become wobbly.
Yeah.
Somebody else had a hand. Yes.
Wouldn't you have to require more energy for when it's outside than when it's inside?
So you immediately begin to see the problem. So where you compute this moment of inertia matters. So now the formula would still be the same. The formula would still be 1/2 I omega squared. But now the moment of inertia that you are taking, instead of taking the moment of inertia for the frisbee through the center, you are now taking the moment of inertia of the frisbee through an edge. And these two moments of inertia may not be the same. Yes?
How would the formula be the same? Because when you're rotating the center of the disc, then the radius.
No, it's not the same.
Oh,
I said the formula is the same. So now you see, over here, suppose this is my frisbee, right? And this is where I put my finger. So this frisbee is rotating. Now if I take any particle here, this is the axis about which it's rotating. So this is Ri. So over here, this is Ri. So if I am summing up, mi times Ri squared for every particle, that number that I will get for I, when I put my finger in the middle, should not necessarily be the same number that I'll get if I put my finger here and the thing is still rotating. Because now this is the axis of rotation, you see, and so this guy is much farther away and this guy is much nearer. And therefore, the Ri's have changed. So how the Ri's come around depends upon the location of the axis. And therefore, when you are talking about the moment of inertia, you got to know the axis of rotation. You cannot ignore the issue of what the axis of rotation is and talk about moment of inertia. So, for example, if you're talking about, let's say, a sphere like the Earth, let's assume the Earth to be a sphere, and let's say for now that the sphere, Earth, is going around an axis to the center, which it is, but the axis is slightly tilted. But let's not worry about that. It turns out that the Earth obviously is rotating, and we know that the Earth has an approximate radius r, and let's say it has some mass n. It turns out that the moment of inertia of a sphere, in this case Earth, with the axis passing through the center, which it is, center is here. If you do the integration and get the numbers correctly, it will be 2/5 mass of the Earth, in this case, or mass of the sphere, times the radius of the sphere squared. So it is a non-trivial quantity that one has to calculate. You will not be calculating them, you will be looking them up. But the fact is that the extended shape of the object comes to play in these problems. It's 2/5 m/r squared. Okay? So, if I take a rod, now if I rotate this sphere about some other point, this number will change. If I take a rod and run something to the middle, and then I rotate the rod, the moment of inertia will be one quantity. Actually, for a rod being rotated through the middle, it's 1/12 through the middle. to this point, A, let's say. 1/12 the mass times the length squared. So this is the length squared. However, if I change the axis to some other point here, then this will no longer be the case, and the moment of inertia would be higher actually. I will not, sorry, it's 1/12. I will not actually work out these things, but I will show you, not today, but I'll show you a trick by which to calculate. If you know the moment of inertia about the center axis, you can actually find out moment of inertia about any axis. There is a very simple theorem by which you can do that calculation. So I'm going to teach you guys the theorem, and next up, I'm going to actually give you a bunch of problems, and we'll do a bunch of problems on Thursday as well, just to get familiar with this part of it. So, just to put it in a manner that is functionally meaningful. Thus far, most of the problems you have done typically required one or two conditions. Generally two conditions. Henceforth, as we get into rotation, most of the problems you'll be doing will be requiring at least three conditions. And this is the reason why I've been repeating so many times that we are notching up the level of this class by a good 50%, because that's how much more difficult materials will become. So I really want you to be on top of this stuff, and I will be giving you a very detailed quiz on everything I've done today on Thursday. Let's go to the quiz for today.